I have introduced the notions of cut time, cut point, and cut locus. The first result I want to present now is about the properties of the cut times. So we fix the setting where we will work. So we will choose to work with the complete manifold, which are connected. We choose a point of the manifold, a vector in TPM of length 1, and we set C to be the cut time of PV. That we know that this is a number in 0 plus infinity. Then if B belongs to 0C, then gamma V restricted to 0B has no conjugate points, and it is the unique unit speed minimizing curve between its endpoints. Second part of the statement, if the cut time is finite, then gamma V restricted to 0C is a minimizing, and one or both of the following statements are true. One, gamma VC is a conjugate to P along gamma v, and 2 there are two or more unit speed minimizing geodesics from P to gamma Vc. Before presenting the proof, let's give a look at the special case when where the manifold is the n-dimensional sphere or radius r equipped with its round metric. So if this is a sphere, and we choose P to be the North Pole, then we have that the cut time C is a pi r, and if we take any b in 0 pi r, then gamma v is a geodesic which has no conjugate points, and it is a unique unit speed minimizing curve between its endpoints. We know that geodesics on the sphere are great circles, and we know that the conjugate point of the North Pole is the South Pole, and any segment of geodesic which is shorter than pi r is minimizing, and it is the unique curve having this property. If we work with this manifold, then this condition is satisfied, and we have that if we take the geodesic segment of length pi r, that is the geodesic segment joining P to minus P, which is a gamma v restricted to 0c, we know it is minimizing. And we have that both of these statements are true, because gamma v pi r, which is the South Pole, is conjugate to the North Pole, and there are two or more unit speed minimizing geodesics joining the North Pole to the South Pole. You can consider the infinitely many geodesics that you get changing the value of the initial velocity vector. So precisely you can consider all these geodesics here. All of them are unit speed minimizing geodesics from P to minus P. Okay, now let's try to prove this result. Unfortunately, I have to erase. So let's prove A. That is, if B is strictly smaller than C, then gamma V restricted to 0B has no conjugate points, and it is a unique unit speed minimizing curve. So suppose that P belongs to the open interval 0C, then by definition of the cut time, so T cut PV implies that there exists B prime with B smaller than B prime is more than C, such that gamma V restricted to 0 B prime is minimizing. Then this implies that gamma V T cannot be conjugate to P along gamma V for T in 0B. This interval is closed on the right. This follows from the fact that we have a theorem which says that if we have a conjugate point, then the curve is not minimizing. And gamma V restricted to 0B is minimizing. Why this is true? If there exists a shorter admissible curve between P and gamma VB, then we could combine this curve with gamma V restricted to B prime, and we would obtain a shorter admissible curve from P to gamma V B prime, and this would contradict the fact that gamma V restricted to 0 B prime is minimizing. So we proved that gamma V restricted to 0B is minimizing. Now we have to prove that it is unique. Okay, suppose by contradiction that sigma is another minimizing curve of unit speed. We start observing that sigma prime B is different from gamma V prime B. The reason why this is true is that if here we would have we had equality, this combined with this would prove that sigma coincides with gamma v, and this is not possible. Now we can define a new unit speed admissible curve gamma tilde which is equal to sigma t for t in 0b and gamma vt for t in bb prime. It is clear that since this is minimizing and this is minimizing, the length of gamma tilde is b prime. So this says that it is minimizing from p to gamma v b prime, but this curve is not smooth. At t equal b. Why? Because before we proved that sigma prime at b is not equal to gamma v prime at b. So this would contradict the smoothness of minimizing curves. Precisely, we know that minimizing curves are smooth geodesics, so we got a contradiction. So we proved the statement A of the proposition. Now we have to prove the statement B. I will write it here again. So if C is finite, if the cut time is finite, then gamma V restricted to 0C is minimizing, and one or both the following statements are true. Gamma VC is conjugate to P, and two, there are two or more unit speed minimizing geodesics. From P to gamma VC. Okay, let's assume that the cut time is finite. So C is finite. By definition, of the cut time, there exists a sequence Bi with Bi tending to C minus, increasing, such that gamma V restricted to 0 Bi is minimizing. The distance function is continuous, so distance and this implies that if you take the distance between P and gamma V Bi and you take the limit as I tends to infinity, from one side this is equal to the distance between P and gamma VC. From the other side, this is a limit as I tends to infinity of Bi, which is C. So we prove that the distance between P and gamma VC is exactly C. This implies that gamma V restricted to 0 C is minimizing. So now it remains to prove that one or both of these two statements are true. So we have to prove that gamma VC is conjugate to P, and there are two or more unit speed minimizing geodesics. Okay, suppose that gamma VC is not conjugate to P. If gamma VC is conjugate to P, there is nothing to prove. Let's show that this implies there exists a second unit speed minimizing geodesic from P to gamma VC. So let Bi denote a sequence such that Bi tend to C from the right, so Bi decreases to C. And by definition of T cat PV implies that gamma V restricted to 0 Bi is not minimizing. So this means that for each I there exists a unit speed minimizing geodesic sigma I of this form, satisfying sigma I at 0 equals P, sigma I AI equal gamma V Bi. And AI is smaller than Bi. We set Wi to be sigma prime I at 0. Clearly this is a unit vector. So by compactness of the unit sphere, we can suppose that Wi belongs to Sn in TPM. Sorry, I should use TPN minus 1. Then there exists a subsequence that I will call Wi, so I will not change the name, which converge to W, which is of course a vector of length 1. We have that the AI are positive and AI are bounded by Bi. Then we can easily see that there exists a subsequence that I will call AI, which converges to some number A. Now we use the continuity of the exponential map. And we get that sigma I AI, that is exponential map evaluated at AI Wi, converges to the exponential map evaluated at AW. But we know also that sigma I AI is also equal to gamma VBI. And we know that gamma VBI converges to gamma VC. So we proved that exponential map evaluated at AW coincide with gamma VC. We can use again the continuity of the distance function and look at this distance. If you take the limit, from one side we get that this is the distance between P and gamma Vc, which is equal to C, but from the other side this is equal to the limit as I tends to infinity of AI, which is equal to A. So A is equal to C. So if this is true, then if we take the curve sigma defined by sigma t equal exponential evaluated at tw, this is also a unit speed and minimizing. From P to gamma Vc, because its length is exactly C, which is the distance between P and gamma Vc. So we constructed a new curve. It remains to prove that sigma is different from gamma V. So now we use the assumption that gamma Vc is not conjugate to P. This implies that CV is a regular point of the exponential map. There is a proposition which establishes the relationship between conjugate points and the regular points, and critical points of the exponential map. So if we have that gamma VC is not conjugate, then CV is not a critical point, which means it's a regular point. So this implies that the exponential map is injective in some neighborhood V of CV. Now we observe that we have this identity for each I. This follows from the fact that sigma I AI is equal to gamma VBI. So this identity is equivalent to this one. Instead, AI WI is different from BI V because WI and V are unit vectors, but AI is smaller than BI. I wrote it somewhere at the beginning. So since BIV converges to CV, then BIV belongs to V if I is enough large. Sorry. Let's write just this way to save space. And by injectivity, AI WI does not belong to V for these values of I. So therefore, we have that CW equal limit as I tends to infinity of AI WI different from CV. This implies that W is different from V, and this implies that sigma is different from gamma V. And this is the end of the proof. Okay, then let me check how much time I have. 147. Okay, so let's now try to study the cut locus. In order to do this, I have to introduce some definitions and one theorem. Let's start with definition of unit tangent bundle. UTM. This is given by the element of the tangent space such that the length of V is 1. It's possible to prove the following theorem. Suppose that MG is complete, is connected, then the function T cut defined on the unit tangent bundle to 0 plus infinity is continuous. I leave to you the details of the proof. Essentially, the idea of the proof is that you take PV in UTM, you set a sequence converging to PV. You set Ci equal T cut of Pi Vi, and then you take the limit of Ci and the lim sup. What we have to prove is that Ci tends to C, and this is done proving that you have this chain of inequalities. I prefer to skip the details of the proof. I will leave them to you, and I prefer to choose to prove a theorem about the cut locus. So I need other definitions. So given P in the Riemannian manifold M, we define the tangent cut locus of P as the subset of TPM such that the length of each element is equal to the cut time at P V over length of V. And we have also the injectivity domain of P defined this way. The definitions look similar. The difference is that here you have the identity and here you have an inequality. It is immediate to get that this is the boundary of ITP and that the cut locus at P is the exponential map restricted at P evaluated at PCL P. Why? Because the points in cut locus of P are of the form gamma V at T cut. And we know that the cut time does not depend on the length of the vectors, so we can work with geodesics having length 1, speed 1, sorry. So let Mg be a complete connected Riemannian manifold, and let's fix a point P of M. Then we have three statements. The cut locus at P is a closed subset of measure 0 B. The restriction of the restricted exponential map to the closure of the injectivity domain at P is surjective. see the restriction of the restricted exponential map to the injectivity domain at P. The difference with this is that here we take the closure is a diffeomorphism onto M minus cut locus at P. Let's start with the proof of A. This is the longest among these three. Among the three proofs. So suppose that Qi is a sequence of points in cut locus of P such that Qi converges to Q in M. So we can write Qi as the exponential map evaluated at T cut P Vi Vi, where Vi are vectors of length 1. So Vi belong to a sphere which is compact, so there exists a subsequence that I will call Vi, which converges to V. Now we use a previous theorem and we can write T cut P V as the limit as I tends to infinity of T cut PVI. So this follows from the fact that the cut time is a continuous map. Convergent sequences in a metric space are bounded so the sequence T cut PVI is bounded. This implies that T cut PV is finite. Now we use the fact that the exponential map is continuous and this implies that Q must coincide with the exponential map evaluated at T cut PV. So this implies that Q belongs to the cut locus of P implies cut locus closed. So this is a proof of the fact that the cut locus is closed. It remains to prove that it is of measure 0. So choose any polar coordinates theta 1, theta 2, theta n minus 1 r on TPM. Clearly, TCLP, maybe it's a good idea to write down definition again. So this is defined as V in TPM, such that the length of V is equal to cut time at PV over length of V. So this is the definition. This implies that TCL at P is locally the graph of the continuous function R equal T cut of at P theta 1 theta n the reason why the function has this form is that the first n minus 1, the first n minus 1 coordinates are used for identifying the vector which is supposed to be of length 1, and R is the coordinate which gives you the length of the vector. So you have a function of this form. So graphs of this kind of functions, let's write of continuous functions have measure 0. This is a result contained in the book by John Lee, Introduction to Smooth Manifold. Precisely is proposition 6.3. So this implies that TCLP is the union on with I in I with I finite set of indices of, let's write Wi with measure of Wi equals 0. Here Wi is a graph, one of the graph of this form. Now we use the fact that smooth maps take measure 0 sets to measure 0 sets. Once again, you can find this result in the book by John Lee, Introduction to Smooth Manifolds, proposition 6.4. Consequently, the cut locus at P, which is given by this identity, has a measure 0. So this is the proof of the statement A. I want to recall the statement B. So B was the statement about the restriction of the exponential map to the closure of the injectivity domain. The proof of this is easy. Just use the fact that every point in M can be connected to P by minimizing geodesic. This follows from the fact that the manifold is complete. To prove C, that is this restriction is a diffeomorphism, instead we have to work a bit. So first of all, it follows from the definition that this is M minus cut locus of P. The definition of the injectivity domain implies that no point in exp P I D P can be a cut point. So we have that no such point can be a conjugate point. So since there are no cut points, then we have that the exponential map is injective on injectivity domain at P. Instead, the absence of conjugate point implies that the exponential map is a local diffeomorphism on the same set. If we combine the injectivity with the fact that it's a local diffeomorphism, then we have exp is a diffeomorphism on the injectivity domain. I want to present without proof a corollary of this result. This corollary is about compact manifolds, and it says that every compact connected smooth N manifold is homeomorphic to a quotient of the closure of the unit ball Bn by an equivalence relation which identifies only points on the boundary The last result I want to present is about the injectivity radius. So the definition was as follows. This was a supremum of O A positive such that the exponential map is a diffeomorphism from BA0 to its image. The following result says that the injectivity radius is related to the cut locus. So let Mg be a complete connected Riemannian manifold for each P in M. The injectivity radius at P is the distance from P to its cut locus if the cut locus is non-empty. And infinite otherwise. How to prove this result? So fix P in M, then let's denote D as the distance between P and its cut locus. D is equal to plus infinity if the cut locus is empty. Fix A in 0 infinity in an arbitrary way, and let the BA denote the the set of vectors of length bounded by A. If A is plus infinity, then we get TPM. So now we have to show that the restriction of the exponential map to BA is a diffeomorphism onto its image if and only if A is smaller or equal to D. If we prove this, then the result follows. So suppose that A is smaller or equal to D, then from the definition of D, we have that no point of the form exponential evaluated at V with V in BA is no point of this form is an element of the cut point. Excuse me. No point of this form can be a cut point. I'm sorry for the confusion. This implies that BA is contained or is equal to IDP. Now we can use the last theorem, the one I proved. So statement C of last theorem implies that this is a diffeomorphism. Why? Because the restriction of the exponential map to this set is a diffeomorphism. So it is true also if we replace IDP with BA, which is contained in IDP. Now, suppose that A is larger than D. That is, this is not true. Then we have that P has a cut point Q such that distance between P and Q is strictly smaller than A. From the definition of cut points, it follows that radial geodesic from P to Q are not minimizing past Q. So we can use proposition 6.11, which says that if you have a point on a manifold and another point Q in a geodesic ball centered at the first point, then up to a reparametrization, the radial geodesic from P to Q is a unique minimizing curve in M from P to Q. So this says that there is no geodesic ball of radius greater than distance between P and Q. In particular, this says that the restriction of this map to BA is not a diffeomorphism. And this is not possible. This is the end of the proof. Okay, then it's time to stop.